Very good evening. Welcome to day 7 of our 10-day short course program on metrology and mechanical measurements. Today, we are going to discuss a very important topic in engineering metrology, errors in measurement and uncertainty. The focus of this session is to understand why measurements are never perfectly exact, how different types of error arise during measurement, how measurement uncertainty is evaluated, and how uncertainty influences engineering decisions. As highlighted in today's presentation, understanding errors is the first basic step towards producing trustworthy and defensible measurement data. In precision engineering, manufacturing, inspection, calibration, and quality control, measurement plays a vital role. However, no measurement can be considered perfectly exact. Every measurement value contains some degree of deviation from the ideal or true value. Therefore, an engineer must understand not only the measured value but also the possible error and uncertainty associated with that value. Today's session takes us from the fundamentals of measurement errors to advanced uncertainty evaluation, supporting by practical engineering case studies. So we will discuss the session overview for today's segment. In this session, we will cover 6 major areas. First, we will understand measurement and error. Second, we will study the 3 major types of measurement errors, say gross error, systematic error, and random error. Third, we will study the various sources of errors, including instruments, environment, human factors, and measurement processes. Fourth, we will distinguish between accuracy and precision. Fifth, we will learn about the measurement uncertainty, including type A and type B evaluation, combined uncertainty, and expanded uncertainty. Finally, we will examine 2 engineering case studies involving a digital micrometer and a coordinated measuring machine. Let us now proceed as per the session agenda. Let us begin with the fundamental concept. No measurement is ever exact in nature. Every measured value differs, however, slightly from the true value of the quantity being measured. We can represent this concept simply as measured value equal to true value plus or minus error. The true value is an ideal value that cannot normally be known exactly. Instead, we estimate it using appropriate measurement methods and reference standards. The measured value is the value actually obtained from the instrument or observation. The difference between these values represents measurement error. Therefore, understanding, controlling, and quantifying error is fundamental to reliable metrology. Measurement errors can be broadly classified into 3 major categories: gross errors, systematic errors, and random errors. Gross errors are generally large and avoidable mistakes. They may occur because of carelessness, incorrect reading of a scale, incorrect recording, or improper use of an instrument. Systematic errors are consistent and repeatable. They normally arise from a fixed cause, such as instrument error, environmental conditions, or the measurement method. Random errors are unpredictable fluctuations that occur because of uncontrollable variations in the measurement process. Understanding this classification helps the engineers to decide how an error should be identified, controlled, corrected, or statistically treated. Let us deep dive into the various types of errors. First one, let us go with systematic errors. Let us now look more closely at systematic errors. Systematic errors are predictable and correctable. They can originate from several sources. Instrumental errors may result from own components, zero error, poor calibration, or manufacturing tolerances. Environmental errors may be treated by influencing following parameters like temperature, humidity, vibration, dust, or pressure variations. Observational errors may result from parallax error, repeated reading habits, or observer reaction time bias. There may also be theoretical or method related errors resulting from simplifying assumptions in a measurement method or mathematical model. An important characteristics of a systematic error is that it tends to bias measurement in the same direction. Therefore, systematic errors can often be identified and reduced through calibration, correction factors, and improved measurement procedures. Let us now go through the next classification of errors, random errors. Consider random error. Random error arises from unpredictable variations in the observer, instrument, workpiece, or environment. They may be positive in one measurement and negative in another measurement. Unlike systematic errors, random errors cannot normally be completely eliminated. However, they can be reduced or statistically estimated. Repeated measurements are therefore very important. When several readings are taken, individual values generally cluster around a mean value. Statistical parameters such as the mean, standard deviation, and standard error help us to understand the behavior of random measurement variation. This is why repeated measurements and statistical analysis are essential in precision metrology. Sources of measurement errors. Errors can originate from different parts of the measurement system. The first source is the instrument, calibration drift, wear, limited resolution, non-linearity, and backlash can influence the result. Second source is the environment, temperature, humidity, variation due to vibration, air pressure, dust, and lighting can affect measurement accuracy. Third source is human observer that may lead to parallax error, fatigue, reading technique, and unfamiliarity with the instrument can introduce errors. Fourth source is measurement process or setup. Improper fixturing, misalignment, workpiece condition, and excessive or insufficient measuring force can influence the final result. Therefore, reliable measurement requires control of the complete measurement system, not just the measuring instrument. Let us now discuss the discrimination between accuracy and precision in measurement. A very important distinction in metrology is the difference between accuracy and precision. Accuracy refers to the closeness of a measured value to the true value. Precision refers to the closeness among repeated measurements. An instrument may produce readings that are very close to one another but consistently different from the true value. Such a system is more precise but not accurate. Similarly, measurements may be distributed around the true value but show considerable variation. For reliable engineering decisions, we ideally need both high accuracy and high precision. This distinction is particularly important in calibration, inspection, quality control, and research measurements. Let us now go through the importance of measurement uncertainty. Now we move from measurement error to one of the most important concepts in modern metrology, measurement uncertainty. Measurement uncertainty is a parameter associated with the measurement result that characterizes the dispersion of values that would reasonably be attributed to the quantity being measured. In simple terms, I can say error is something we cannot know exactly, whereas uncertainty represents what we can quantify about the doubt in our measurement result. Uncertainty is generally expressed as an internal thing rather than a single number. For example, a measurement may be reported as L, length is equal to 25.02 millimeter plus or minus 0.03 millimeter with a given tolerance. When a coverage factor of approximately 2 is used, the expanded uncertainty is commonly associated with a confidence level of approximately 95% depending on the evaluation conditions. Therefore, measurement uncertainty provides essential information for calibration certificates, inspection reports, and conformity decisions. Let us now discuss about type A and type B uncertainty. The measurement uncertainty can be evaluated using two principal approaches, type A and type B evaluation. Type A uncertainty is evaluated using statistical analysis of repeated observation. For example, when repeated measurements are available, the standard uncertainty can be estimated from the standard deviation of the mean. The presentation gives the following relationship. UA is equal to S divided by root of N, where S represents the standard deviation and N represents the number of observation. As the number of repeated observation increases, the statistical estimate generally improves. The type B uncertainty is evaluated by methods rather than statistical analysis of repeated observation. Sources may include calibration certificates, manufacturer specifications, previous measurement experience, instrument resolution, specified tolerances, and reference standards. Engineering judgment and appropriate probability distributions may be used in type B evaluation. Once the individual uncertainty components have been evaluated, they must be combined. The combined standard uncertainty is calculated by combining the individual uncertainty contributions using root sum square method. The presentation expresses the following equation as illustrated below. The combined uncertainty may include contributions from both type A and type B sources. We then calculate the expanded uncertainty using the following empirical relationship as illustrated below. Here in this equation, K is the coverage factor. A coverage factor of approximately 2 is commonly used for an interval corresponding to roughly 95% confidence under approximate assumptions. The uncertainty budget presented in today's session highlights the contribution from repeatability, instrument calibration, or instrument resolution, and thermal expansion. Let us apply these basic concepts to a practical engineering example. Consider the case study of digital micrometer, 25 millimeter gauge block, which was measured 10 times using a digital micrometer with a resolution of 0.001 mm. The purpose is to verify the compliance with an engineering tolerance of plus or minus 0.02 mm. The uncertainty budget considers several contributors. These include the repeatability of the 10 measurements, the instrument resolution, the calibration certificate uncertainty, and thermal expansion caused by a temperature difference from the reference condition. The resulting measurement is reported as 25.021 millimeter plus or minus 0.013 millimeter with a coverage factor of 2. According to the case study, the part is within the tolerance and can therefore be accepted with a documented confidence level. An important lesson here is that calibration and repeatability are the significant contributors to the uncertainty budget, and therefore they provide useful targets for improvement. Our second case study involves coordinate measuring mission. A precision housing bore has a nominal diameter of 50 millimeter with a tolerance of plus or minus 0.010 mm. The CMM repeatedly measures the bore as 50.018 mm, which indicates an oversized condition. An investigation reveals two important factors. First thing, the probe stylus calibration was 8 months overdue. Second, the component was measured at 28 degrees Celsius rather than 20 degrees Celsius reference condition. The consistent direction of the deviation indicates a systematic error rather than random error. After recalibration and application of the appropriate correction, the bore was re-verified at 50.003 millimeter plus or minus 0.006 millimeter. This case study demonstrates a very important engineering principle. A systematic error should not simply be averaged away. It must be identified, investigated, and corrected. Let us now discuss the importance of measurement uncertainty. Measurement uncertainty directly influences engineering decisions. First, it supports reliable conformity decision, helping us to avoid false acceptance and false rejection of tolerance critical components. Second thing, it supports process control by helping us to distinguish genuine process drift from natural random variation. Third, it supports traceability and audits because calibration and measurement reports need to communicate the associated uncertainty. Finally, uncertainty is important in design margins because tolerance and safety factors must be considered together with the capability and limitations of the measurement system. Therefore, uncertainty is not merely a mathematical exercise, it is an essential part of the engineering decision making. Let us summarize the major lessons from today's segment. First, measurement errors carry some degree of error. These errors may be gross, systematic, or random in nature. Second, systematic errors create consistent bias and can often be corrected, while random errors are normally treated using statistical methods. Third, accuracy and precision are different concepts. Accuracy relates to closeness to the true value, while precision relates to repeatability. Fourth, measurement uncertainty quantifies the doubt associated with the measurement result. The type A and type B uncertainty contributions are combined and the result can be expanded using an appropriate coverage factor. Finally, our case studies demonstrate that a properly documented uncertainty budget transforms a simple measurement value into a defensible engineering decision. So, with this above message, we come to the conclusion of day 7 of our 10-day short course program on metrology and mechanical measurements. I hope this session has helped you to develop a clear understanding of measurement errors, their sources, accuracy, precision, uncertainty evaluation, and uncertainty budget. Remember one thing: accurate method, accurate measurements leads to reliable data, and reliable data leads to better engineering decisions. Thank you for joining the today's session. Stay connected, keep learning, and continue your journey towards excellence in metrology and mechanical measurements. Thank you all.